streaming on this side, that way I can do the pause without having to worry too much about it. One second. Share my screen with the talk. You see the talk there, right? On this side, that way I can do the pause. There. See, otherwise, the thing is, there's 30-second delay from the other one. I have to make sure that I delay it, otherwise it's impossible. My official timer is my iPhone, so no. You guys can see that, yeah. So as I said, as soon as I start, as soon as I stop, I'll stop sharing, and then you'll share it back. Okay. Oh, did I? Is my my video is stopped? Yeah. Okay. Video. Okay. Let me turn on the video then. Nothing there. Okay. Okay. Oh, don't try it. Okay. I think this is 3 o'clock, so thank you and welcome everybody back to the online SPICE-SPIN+X seminar series. As you all know, this is a webinar format. I organized this webinars together with Libor Schmekiel, Angela Wittmann here in Mainz, and Karen Eversosite in Duisburg, in collaboration with the SPIN+X Collaborative Research Center, led by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern, and Matthias Chloe here in Mainz. Just so you know, because we have different seminars coming up. Next week, there's going to be, well, in another, not next week, I think next week, sorry, next week, Claria Donnelly. And then whenever we have, of course, other overlapping conferences, we don't have them. So please check out the schedule. It is now pretty full for the rest of the summer. So it's my pleasure to welcome Dr. Nikolai Kiselev to give a talk today. He's a scientist at the Forschung Zentrum Jülich. He got his PhD in Dresden in 2010 in Germany, but then his master's in Ukraine in I cannot pronounce that, Slaviansk State Technological University. And he works on two-dimensional systems, but on three-dimensional topological magnetic solid-tone systems, looking at hopfions, fermions, all kinds of topological textures, and has done a lot of modeling to atomistic simulations, going beyond the Heisenberg model. And then now he's even getting into OpenGL and all kinds of stuff. So with this, I'll stop sharing, and I will ask you to please, yeah, go ahead and start your presentation. Go ahead and share your screen. Perfect, we see it. So go ahead and start whenever you like.
Okay. Hello, everyone. I hope you all can hear me. Yep. So my talk will be not exclusively about this recent paper we published on magnetic hopfion rings, but more about magnetic hopfions in general. So first of all, I would like to start with acknowledgement to a bunch of very important people. Yep. First of all, that is the group of experimentalists from Ernst Ruska Center for Microscopy and Spectroscopy with Electrons. The head of this unit is Professor Rafael Dunin-Barkovsky, our long-term collaborator from China, from High Magnetic Field Lab -2, who provides the super high quality samples for us. So the team of theoreticians from the Peter Grünberg Institute and the Forschung Zentrum Jülich, Professor Borisov, Professor Melcher, and especially I would like to highlight the contribution of the Fenshan Zhen and Philippe Rybakov to this project. So Fenshan did most of the experimental results which I will present today, and Philippe contributed to theoretical part on all levels, starting from homotopy group analysis and ending with the software development. So that's the outline of my talk. I will start with the short introduction with the aim to answer the question, what are magnetic hopfions? And then I will discuss two distinct systems, in particular hopfions in frustrated magnets and hopfions in chiral magnets. The only two systems where we so far expect and know hopfions can exist. And with that, I will conclude my talk. So let's start from the definition. So what are magnetic hopfions? So magnetic hopfions is a particular type of magnetic textures, which can be called as three-dimensional topological solitons, which means that they are well localized in all three dimensions, and they can move and interact with each other as ordinary particles. So here on the left, you can see an example of the simplest hopfion is the topological charge 1 and corresponding cross-section of this magnetic texture. And here you can see a couple of other more complicated magnetic hopfions. So a distinctive property of magnetic hopfions is the linkage of so-called pre-images or fibers. So every fiber is the collection of points, the closed loop of where magnetization is pointed in the same direction. For instance, this red fiber and the green fiber, they are linked as elements of a chain. And this provides the topological property to this texture, meaning that it cannot be continuously unwound into a collinear ferromagnetic texture. So there are a few other names of hopfions. Sometimes they're called countable particles in magnetization field. Recently, I discovered that people also called hopfions as a topological vortex rings, which maybe not the best name because hopfions might be much more complicated than just the ordinary rings, and I will show you a few examples of those. And finally, vortex hopfions can be called as a vortex-like closed strings or knots. So let's start with this pure geometrical definition. So we can take a ordinary pi vortex or skyrmion string and literally bend it and twist the ends of such string in such a way. So you probably noticed that I slightly twisted the ends of this tube to make the linkage between the red and green fibers, for example. So that's a very illustrative and intuitive picture, but it has certain problems, because if you literally follow this way and will try to create hopfion starting from such skyrmion string, you will get a trouble in the center on the axis of bending, because you will get a discontinuity here. So this small trick has to be done to create a hopfion out of pure two-dimensional pi vortex or skyrmion. So we take an ordinary skyrmion, and you know well that if we rotate all the spins about certain arbitrary chosen axis, the continuity of this magnetic texture is not broken, because all the points on the sphere, their relative position with respect to each other remains the same. So we have to rotate magnetization in such a way that the far field, far from the center of a skyrmion, is lying in the plane. And that's an essential step. The next step is not essential, but is useful for the visual purposes. So we have to rotate this plane and place it in ZY plane, for instance. And now we have to rotate this skyrmion about the axis, which necessarily coincide with the direction of magnetization far from the center of the skyrmion. In our case, it is a z-axis. So we rotate this texture as a solid object. And if we would trace now the orientation of the spins in the global reference frame, you will see that all the spins create actually a closed and linked loops. So the fibers of this texture indeed linked. So in this way, we can get the simplest hopfion with the index 1, which is well localized in space and topologically non-trivial. So from the homotopy group analysis, all the texture of this kind can be classified according to the third homotopy group, or with respect to S to sphere, which is the order parameter in this case. And this group has isomorphism to the group of integers, which means that every single hopfion, if it satisfies the criteria to be a topological soliton, can be associated with a particular integer number. This integer number can be calculated with the following invariant, which was introduced by Whitehead many years ago. And this field F is typically called gyro vector field. And the vector field V is a corresponding vector potential of the field F. So alternatively, the Whitehead formula can be written in the following form, which instead of gyro vector, we introduced a curvature vector field. And again, corresponding vector potential of this field. So these two approaches are absolutely equivalent. So how can we create a hopfion with the higher topological index? In the cross-section of this simple hopfion with hop index 1, you can see the position of the vortex and anti-vortex here and here. So in case of hopfion with index 1, we keep the position of these vortices unchanged. But alternatively, we also can rotate them about the center of skyrmons when we produce this revolution of this plane. And following this approach, we can construct the whole diversity of hopfions with positive, negative topological charge, and strictly speaking, up to infinity. It's not a unique, but one of the options we can use to construct hopfions with a different topological charge. It does not guarantee that all this configuration will be stable in any realistic system, but at least this way we can construct these configurations. So in the following, I wanted to discuss the system where this type of magnetic texture can be stable. But before that, I have to mention that everything what I will talk about in my talk has very little relation to a kind of distinct branch of hopfionics, where the aim is to stabilize hopfion via geometrical confinement. So the hopfions and solution for the hopfions, which I will discuss in my talk, characterized by the following facts. So the size of hopfion is much smaller compared to the size of the system, and its stability and its size does not depend on the size of the system. So, and the first in the list is the magnetic system, so-called frustrated magnets. In 2022, we published a paper where we discuss and established the ordinary Heisenberg exchange interaction as a unique interaction, which can by itself be responsible for stability of magnetic hopfions. Which means that if you have a magnetic Hamiltonian, which is composed of just a single interaction, Heisenberg exchange interaction, is already enough to have all this diversity of different solutions. Of course, there are a few restrictions. For instance, in case of cubic crystal, you have to have at least 4 interacting shells or more. In principle, you might guess that these parameters probably are not realistic. That's why we never observed hopfions and frustrated magnets so far. But that's not the case. Here you can see a typical example for the minimalistic model, which composed of only 4 shells. And you see that the nearest neighbor exchange interaction, the second shell, third shell, and fourth shell decay with the distance. They might change the sign. So in principle, this behavior is absolutely identical to what we would expect to see in realistic material. So since in principle, this model allows the infinite number of shells, it's not very convenient to work with such a model. And because of that, we do an expansion of this term into a continuum limit, into micromagnetic model. We do this by Taylor expansion of this term, assuming that the angle between neighboring spins is very small. And contrary to ordinary micromagnetic model, where we take only the first term of the Taylor expansion, which corresponds to this so-called exchange stiffness term, we take a higher order terms up to the fourth order. So which in case of cubic chiral crystal will give rise to two additional terms with corresponding additional micromagnetic constants B and C. So all the A, B, and C micromagnetic constants are nothing else than a linear combination of exchange coupling constants from the spin lattice Heisenberg model with appropriate prefactors, which itself depend on the symmetry of the crystal. And following the Dirac-Hobart approach, we can immediately give an answer what is the necessary but not sufficient condition for the hopfion existence in this model. And it's very simple, so all three parameters should be positive. Because of the negative sign here, it immediately implies that some of your JJ coupling constants should be positive and some of them should be negative. Otherwise, you will not be able to satisfy this criteria. So let's plug this functional in micromagnetic software, insert the initial configuration in form of toroidal shape hopfion ansatz with the hopfion index 7, and let system to relax and find the closest local energy minima. So using conjugate gradient method, we can converge to a local minimum very quickly. We're almost done, and you see that this configuration did not change much from the initial state. Okay, it's quite distorted, but it's still a single loop with additional twisting on this hopfion. Alternatively, we can create the same hopfion with the index 7 by placing next to each other two hopfions with the index 3 and 4. So when we start, let them interact and minimize the energy, the hopfions starts to merge, fuse together, and create a completely different texture to what we saw in the previous movie. So this two hopfions are this single hopfion represents a kind of two hopfions which are linked to itself. So it means that in principle, every topological sector, meaning that for every topological index, we can find at least a few different configurations with the different energies. And in this case, a typical question, fundamental question, which you have to ask to your model, how the lowest energy bound look like and what kind of functional dependence it has with respect to topological index of your solitons. So in our paper, we provide the answer to this question and prove that lower energy bound limit in this model has a power law dependence, meaning that the energy is proportional to the hopfion index in the power 3/4, and which is surprisingly coincide with the behavior of hopfions in Skirum-Faddeev model, the first model of the unit three-dimensional vector field, which has nothing to do, unfortunately, with magnetism and any magnetic materials, but which was the first model where magnetic hopfions in unit vector field has been discovered. Here you see a first 7 hopfion configuration, which corresponds to lowest energy state on these dependencies, identified by means of numerical energy minimization. So this type of lower energy bound behavior has a very interesting implication. In particular, it can explain why hopfions in the previous movie start to and tend to merge and fuse together. So if we take the energy of hopfion with the topological index 3 and the hopfion with topological index 4 and sum their energies, so the energy of non-interacting hopfions is much higher than the lower energy bound limit. So it means that such magnetic texture with total topological index 7 in principle has a chance to reduce its energy by fusion of these hopfions. And this explains why this interacting hopfion stands to merge together and create a more complicated texture, which is not the case, as many of you know. For instance, in the case of two-dimensional chiral magnets, skirmions, they are not tending to merge and create more complicated textures, for instance. Before I continue to chiral magnets, the only thing which I have to say about frustrated magnets, it's very promising and very interesting model, and many interesting aspects of this model still has to be discovered. The only disadvantage so far is that we did not observe hopfions in this system experimentally, and honestly saying, we don't have a good candidate of the system where this model can be realized and where we might expect to observe such hopfions. Instead, we observe hopfions in chiral magnets, in those systems which we study for a long time. So I have to start with a short introduction to what chiral magnets are. So chiral magnets, in particular in my talk, I will talk about isotropic chiral magnets, cubic chiral magnets. It's a particular type of magnetic crystals which characterized by the specific type of crystal symmetry without center of inversion, which give rise to isotropic bulk type Zaleshinsky-Mori interaction. The competition of this type of DMI with the Heisenberg exchange interaction give rise to a helical spin spiral as the ground state of the system. So strictly speaking, due to the isotropic properties, the ground state of the system represents a multi-domain state, where every domain characterized by a helical spin spiral with k vector pointed in a certain direction. And when we apply a magnetic field to such system, it quite quickly converges to a monodomain state, where all domains, the k vector of all domains pointed in the direction of applied magnetic field, and all spins are slightly tilted towards the external field, which creates so-called conical phase, which dominates in the whole intermediate range of magnetic fields. And the chiral magnets are also very well known from the fact that they are able to host magnetic skirmions, especially when the sample is cut in shape of thin plate. So here you see an example of Lorentz-TM images of ferrum germanium lamella with approximately 1 micron width and 180 nanometers thick. So with increasing magnetic field, you can observe a transition between the helical spin spirals and cluster of individual skirmions. Iron germanium is one of our most favorite type of chiral magnets because it has, among all other B20 type crystals, the highest TC. And we work on it for many years, and we quite well understand what is going on in this material. So here you see a list of our publication within last 6-7 years. So you should believe me in words that we are kind of experts on this material. And for us, it was especially unexpected to observe hopfions in this system, especially because we know for sure that isolated hopfions, when you simulate them in this system, always collapse, irrespective of what kind of initial gas you insert there, what kind of magnetic field you apply, and so on. So the secret answer to the question how to stabilize hopfions in this system was that you have to place inside such a hopfion ring at least one skirmion string. That's how the appearance of such rings around skirmion string look like in Lorentz-TM images. So the first image illustrates the appearance of the edge modulation at the edges of our sample, which appear due to applying a cycles of positive and negative magnetic field with respect to the normal of the sample. So you can see that as soon as we observe such edge modulation, we can gradually increase magnetic field, which leads to a contraction of this circle towards the center, and finally it stops around such skirmons inside. So this movie illustrates another approach where we start not from the isolated skirmons, but from the labyrinth helical texture. We apply a few cycles of positive and negative magnetic field, which give rise to appearance of the edge modulation, which propagate towards the center of the sample. Let's watch it once again. So after a few cycles, we can observe appearance of the closed loops here. As soon as we observe them, we can start to gradually increase the field. And with high probability, we can up with a certain configuration similar to what you see right now with the bright ring and a few bright spots in the center, which corresponds to a hopfion ring and skirmon string inside. So following this approach, we succeeded to capture the whole diversity of different configurations with different number of skirmons inside, varying from 1 up to 12. We also captured the in-field evolution of this configuration. So in this case, each row corresponds to each individual series of images, with magnetic field increasing from left to right. And what you can see here is that with increasing field, the intensity of the contrast from such a ring is getting weaker and weaker with increasing field. And the distance between skirmons inside such a ring is drastically decrease. So as soon as we reach a certain critical field and such ring disappear, the skirmons immediately run away from each other. So which means that this ring literally acts as a belt which ties all skirmons inside together. So here you see a bunch of very exotic configurations. And the first row corresponds to experimental images, and the bottom one corresponds to images reproduced from micromagnetic simulations. As you can see, we get a perfect agreement. I want to emphasize that we don't do any fitting here. We simply use the same value of external magnetic field, the same geometry of the sample as in experiment, and a set of material parameters which we identified in our previous works on iron germanium. We plug all that in our micromagnetic software, and by simply constructing appropriate initial configuration, we were able to reproduce all this configuration. In the following, I would like to focus especially on this configuration where we have just one ring and one or a few skirmons inside. So here you can see results of micromagnetic simulations, starting with 3 different initial configurations, so we can construct this hopfion starting from simply placing up and down domains in the center of our simulated domain, and surround all that by the conical modulation. In state 1A, the conical modulation has an additional twist, which forms kind of a vortex state with the center, which coincides with the skirmon string. And in state 1B, this conical state is more or less homogeneous across the whole sample. In state 2, we have a single skirmon string and kind of a hopfion ring which extends across the whole thickness of the sample up to the surface. We can compare the results of these micromagnetic simulations to experimental observation. The first row of images corresponds to theoretical Lorentz-TM images calculated for corresponding magnetic textures. And the bottom row of images corresponds to experimentally observed contrast. So we immediately see that such a perfect ring we observe always when this conical vortex state has a center which coincides with the position of the hopfion ring. When hopfion ring on the Skirman string is surrounded by more or less homogeneous conical face. We have an additional bump on the either surface of such hopfion ring, which results in also bumps on the Lorentz stem images, which are seen not only on our theoretical images, but also on experimental images as well. And such configuration was really hard to get. We do not observe it. Actually, in our experiment, such configuration has been observed only in the case when this object is located close to the edges and has an additional skirmal next to it. In principle, such configuration is also very unstable. Also in our micromagnetic simulation, any small tilting of the field, any small perturbation would lead to convergence of this state to such more compact hopfion ring, which is quite reasonable from the point of view of Zeeman energy term, which would like to compress the area occupied by magnetization pointed against the applied magnetic field. So to quantify this effect, we use a more advanced technique, which is called electron holography. So here you see a phase shift image, which was obtained with electron holography experiment. And the intensity of this image, contrary to Lorentz images, can be quantified in units of radians. And also can be used to reconstruct in-plane component of induction field of the sample. So using this technique, we can compare the profile of experimentally measured images and theoretically calculated ones. So at identical condition, the same field, and starting with nearly with a similar initial configuration, we obtain this state in our micromagnetic simulations and can compare the profile of phase shift signal of experimental and theoretical images. As you can see, it follows and reproduces each other quite well. We are very happy with how well agreed this data. And here you see isosurface representation of this configuration. So from the point of homotopy group analysis, all this configuration can be described in terms of group, which represents a direct product of a second homotopy group of S2 sphere and the third homotopy group, which means that every configuration of that type should be, in general, described by two integer numbers, two topological charges, Q and H, Skirman topological charge and the hopfion topological charge. So it's not surprising that this configuration with a single Skirman string and the hopfion ring around has a topological charge -1 and 1. But here, where we have 11 Skirman strings, we have hopfion index 21, which was quite confusing for some the readers of our paper. And I will try in the following 2 slides briefly explain the reason for such a huge topological index of the hopfion charge here. So in the supplementary material of our paper, we provide this homotopy between the isolated hopfion and isolated Skirman string and a linked hopfion with this Skirman string. So it is quite surprising that such homotopy exists, but it is. And what I want to draw your attention is to what is going on with the texture of this hopfion when it is linked to a Skirman string. Please watch how the red color and the green color change when we place the hopfion on the Skirman string. So if we compare the initial configuration and the final one, you can see that the color winds in a different direction. So here the red color winds from outside to inside, and here from inside to outside, meaning that the self topological hop index of these rings is opposite. So here it corresponds to -1, and this hopfion ring has a topological charge +1. So it means that if you take hopfion ring from the Skirmion string, you will get a ring which look like a hopfion ring with a twice higher topological charge. So because of that, this configuration, for instance, with the hopfion ring and two Skirmion string inside, if we take these two strings out from the ring, we will end up with the hopfion ring with hop index 3, because each of this Skirmion string give rise to a factor 2 to the hopfion index. We start with the hopfion index -1, and then should add +4. I'm not sure that it's a clear explanation, and because of that, I encourage you to attend the talk which will be given at the end of this month by Philippe Rybakov and the corresponding workshop on nanomagnetism in 3D. We agreed that Philippe will provide a more in-depth explanation of the homotopy group analysis in his talk, and I hope that if you are not able to attend this meeting, you still can see this talk on YouTube afterwards. So instead of diving into homotopy group analysis, I would like to mention that this hopfion rings, according to our micromagnetic simulations, should be also stable configuration in the bulk crystals. And here you see a few examples of such hopfion rings on the single or a bunch of Skirmion strings. Interesting aspect of such solutions is that they have a zero mode, meaning that such a translational rotational motion of hopfion rings along the Skirmion string does not cost any energy to the system, which immediately implies that such rings should be very movable across along the Skirmion string, which hypothetically can find some might be useful for certain applications. So you also might ask the question, where are the hopfion Skirmions with the hop index, with the negative hopfion index, because all the hopfions which I showed you before have a positive hopfion index. So the answer is yes, hopfions can have a negative charge in this case, but they look quite different. So we actually discovered this configuration much earlier with Vladislav Kuchkin, but at that time we did not realize that this configuration actually has a non-zero hopfion index. So this configuration, which we call the hybrid Skirmion tube, is nothing else as just a homotopy of ordinary Skirmion bag, similar to that which is shown on this movie. It turns out that in certain range of parameters, such configuration remains stable, and this knot which you see here represents a stable configuration. And you can manipulate the position of this knot by applying electric current, either along the Skirmion tube or perpendicular to it, which give you opportunity to manipulate and move this object in all three dimensions. So I have 4 more slides in which I would like to draw your attention to another intriguing object which can be stable in chiral magnets, which is called helinoton. So this concept and the solution has been discovered by Tai and Smaluk and with coworkers. And this object basically represents the hopfion, which is kind of linked not to a Skirmion string like in our case, but to helical modulations. More precisely, this hopfion represents can be understood as follows. So let's say we start with the ordinary hopfion in ferromagnetic background. The only difference of these hopfions to those hopfions which I showed you before is that chirality of this hopfion is different in orthogonal directions. So basically, some people would call this crosscut of this hopfion as an anti-skirmionium, if you wish. So then we apply a so-called spiralization procedure. So we basically rotate all the spins around the y-axis on the angle which depends on the position along the y-axis. And that's how we entangle this hopfion with the helical spin spiral and obtain our initial configuration. We let the system to relax, minimize the energy starting from this configuration, and that's the configuration which we obtain after energy minimization. So now we can apply a reverse procedure, so-called despiralization, and we can identify the isosurface and profile of our hopfion. Of course, it's not as perfect as our initial configuration. It's slightly distorted, has a certain weird shape, but it's the ordinary hopfion, as we would expect to see it, for instance, in the model of frustrated magnets. Simply to see it, you have to apply an additional procedure by untwisting the spiral state. So Tai and Smaluk predicts that this object can be easily manipulated, and their motion can be induced by a rotating magnetic field. In the bulk crystals, they create in different clusters. So on our side, we did the following analysis. So we construct the magnetic phase diagram with respect to magnetic field and the thickness of the plate, and calculate with well-established parameters for iron germanium the overfocus and underfocus Lorentz stem images, which we would expect to see in real experiments where we have helioton. So we identify the optimal range of thicknesses where these objects can be found and remain stable even at zero magnetic field. So it corresponds to a thickness range between 100 nanometers and 180. So it's exactly the range where we used to work with iron germanium lamellas. But the only drawback of this concept is that so far we don't know how this configuration can be nucleated. So the laser excitation is one of the possible approach, and we expect that the discovery of helinotons is the second step in the field of magnetic hopfions. So with this, I would like to conclude my talk. So I have a few take-home messages for you. So first one is that we have only a few realistic model of magnetic hopfions. It's basically the model of frustrated magnet and the model of chiral magnets. So we experimentally observe only one type of hopfions in chiral magnets, which represents a kind of exotic type of solutions where hopfions are coupled to Skirman strings. This type of configuration should be described in terms of two integer numbers, two topological charges. The presence of zero mode of such hopfions coupled to Skirman strings might be useful for the practical application in the future. And finally, the helinoton, another type of hopfions entangled with the helical modulations, is a promising direction for the future experimental investigation of the system. That's all. Thank you very much for your kind of attention.
Excellent. Thank you. Thank you, Nikolai. This is fantastic videos, by the way, of really showing how these things come together. That really is, it brings it to life quite well. So now we have the talk open for questions, all about solitons and hopfions. So please raise your hand, and I will let you have the key, question that was actually at the beginning during the talk, but what was eta? But I think it's from Igor Sandalov that refers to one of the parameters that you had in your equations, right? In your phenomenology.
Do you remember the
slide? As I don't know if Igor, maybe I'll bring Igor to online here to see if he means that. And thank you for talking about. We will have those talks on the workshops themselves, just for everybody to know that they are actually immediately online a few days after, not very shortly after. They're online on the YouTube channel because we record them through the system. So Igor, would you like to ask the question? What was the
Yes, thank you. Can you hear me?
Yeah,
Yes.
yeah.
Okay, wonderful. So actually, you've used several constants to make things dimensionals, and it's interesting. You used eta, t, d, and so on. So there are some characteristic constants. Could you comment on them and also comment on the role of boundaries when these hopfions are arising?
Can you say on which slide you saw those numbers?
Well, one constant was on the slide, which is previous before the last TD constant. So you show some plots where there are ratio T to TD. So actually,
that's probably this phase diagram, right?
Yeah, well, question is what are characteristic constants which used in the system in terms of constants which enter Hamilton
Yeah.
and how enter their boundary conditions.
Yep. So this LD parameter and this B critical.
Okay.
Yeah. So this LD is the equilibrium period of the helical spin spirals without external magnetic field. It's zero magnetic field. So it basically equals to the ratio between Heisenberg exchange stiffness and the Zaleshinsky-Moria coupling constant.
Okay.
This critical field here is also a ratio between D and A, but more complicated. It's basically proportional to D square over A. So both of these parameters are coupled to a ratio between Heisenberg exchange stiffness and Zaleshinsky-Moria interaction in this system.
This is bulk characteristics. Where enters boundary conditions of the sample on the sample surface?
So the boundary condition is assumed to be free. So we don't put any any special conditions. We don't pin spins or anything like that.
Yeah, Matthias, you had a question?
Yes, thank you. So really great talk. I have one question. It was on slide 36, the one you showed before. The
6, yep.
36, not 40.
36, sorry.
Yep. Yes. Okay. So here from these Lorentz TM images, can you say something about? So it's like a Skyrmian string, right? That basically has a certain length or goes through the entire sample, and you have the ring which is in a certain height, right?
Yes.
So can you use the depth of field or something to say? Is it at one surface? Is it in the middle of the sample? Is it delocalized? Does it move up and down? Is there something you can say about that?
Yeah, unfortunately, with transmission electron microscopy technique, you cannot say that because electron holography as well as Lorentz microscopy gives you information only about projected induction field. So we cannot say exactly where this Hopfion ring is located, but we can simply judge from the results of micromagnetic simulation. That's why we actually do them, to be able to extract a certain information from the system by not doing experiment or doing certain calculations which we cannot do in the real experiment. And from that, I can tell you that this ring tends to be placed in the middle plane, typically. Especially when it is isolated one. If you have a few rings, like in one of these exotic states, for instance, here or that one, so then there are some nuances where these rings might be kind of displaced. I actually have extra slide with these weird configurations. Yes, it looks like that. So for instance, here you have visually two rings, but actually one of this ring is extended over basically the whole thickness, but slightly twisted. But since you see all that in projected mode, you cannot identify this from the image itself. You can see this only from the reconstruction from the micromagnetic simulations.
And
Of course, there are techniques which allows you to do that, and we would be happy to apply these techniques to visualize our textures as well. The complexity is that the stability of our object requires an external magnetic field, which is in electron microscope is always fixed in the direction, so that the electron beam is always parallel to the applied magnetic field. But for the purpose of electron tomography experiment, you should be able to tilt the field irrespective of the direction of the beam, and that's the major complexity.
Okay. And it's kind of like, so keeping the ring more in the center of the sample, is it like some dipolar effect that causes that?
It's a complex of all the interactions. It's really hard to say that the dipole interaction is only responsible for that. I cannot say that. Most probably the major contribution is again due to the DMI and exchange.
Okay. Thank you.
Yeah.
So we're gonna go first Yaroslav, and then Maria, and then Volodya.
Okay.
So first Yaroslav.
Thank you so much. I have a question about the visualization. So it's probably a simple technical question. If you can go back to one of the first slides where you were showing the rings and
These slides, or
no, just where the 3D ring is shown in colors.
Okay. Like this one.
Like this one, and you had a slide where there were two rings going through each other. I guess my question is, when you do this visualization, what is it easy to determine where this boundary of the ring is? And when you have this picture on the slide you're showing where h is equal to 6, and one says, okay, these are actually two rings, but is it correct to understand that really it's just one structure? You don't have to think about it as two rings going through each other, or and that's probably related to the question of where you draw the boundaries of this ring.
The texture itself. So again, so that here you may answer this question by ask again. So you may decompose these textures on the set of such fibers and try to decompose them. So if you would do it with this texture, you basically have to do it 6 times. So if you will take two arbitrary fibers, let's say a red one and the green one, so you literally have to cut them 6 times to make these two rings unlinked, unchained, so to say. I'm not sure that I properly answer your question, but the criteria is that
I think I can.
Yeah,
It's talking about the mapping, the color mapping that you have. It's not a boundary; it's actually a mapping that you actually twist with boundary conditions, with boundary conditions, and you twist it in the mapping. So you don't need to worry about the boundary itself. It's just mapping in the two-dimensional system.
If you wish, so okay, so all this either surfaces, they represent the position of points where magnetization has only in-plane component. So the z component of these vectors is 0 always. So in principle, this is what we typically identify as the radius of Skirmion, right? Sometimes it's all this is just the question of convention. So in principle, all the edges of this either surfaces you also can identify as the size and the boundaries of these textures.
Just a quick question: is this with Blender that you do this, or with what type of software do you do this animation?
No, I have another favorite software, and I encourage everyone to learn it. It's very old and very useful. It's called PovRay.
Buffering. No, I've seen people using Buffering all the time. That's very good. Yeah, it's just a technical. So go ahead. So, Yaroslav, are you okay with that?
Yeah, thank you. I'm good. Thank you.
Maria, can you please maybe, Karen, maybe unmute yourself, or however you want to do it? Yeah.
Yes. Hello. Thank you very much for the very nice presentation. I have a question about slide number 39.
We're getting there.
39.
39. Yep.
39.
Yes, thank you. So here you show a magnetic texture with a background or a far field, which looks like a vortex to me in the left panels or the right panels. And I believe in your Nature article, you refer to it as a vortex cone configuration.
Yes.
And if I understand your work correctly, you also show that this vortex configuration rotates along the vertical direction. So it's similar to a spiral staircase, or it's a screw dislocation in the magnetic state. And the latter can be described by a quantized Burger's vector. So my question is, do you know of a direct relationship between the quantization of the Burger's vector and the quantization of the Hopf index?
No. Look, example. The answer is very simple. You can see here two configurations. This one and that one. Here we definitely don't have a vortex state, but the Hopf index of this texture is still +1, as well as for that texture. So it means that the far field and the type of the vortex states or the pure conical phase does not contribute to the Hopf index.
Okay, all right, that answers my question. Thank you.
Okay, perfect. Then go next to Volodya. Can you? Yeah, you can also turn on your camera if you like.
Vladimir.
Yeah, Vladimir. Sorry, Vladimir. Sorry.
Now can you hear me?
Yeah.
Yes.
I can hear you.
Yeah. Hello, everyone. My question is about Hopfion index. In the beginning of your talk, you nicely explained us a geometrical meaning of the Hopf charge, which is the linking number between two arbitrary preimages.
Yes.
So it's important to say that this number is independent on which preimages you take. So independent on which two preimages you take, a number is always the same. And
Yes.
this magic is a consequence that infinitely distant points are equivalent. So magnetization in this your first example was always in the same direction in all infinitely distant points. Now, when we consider, this case, for example. Now, when we consider this Hopfion ring with skyrmion string, the infinitely distant points are not equivalent, obviously. And in this case, if you take two preimages which belongs to ring, you will obtain one linking number. If you take two preimages which belong to string, another linking number. If one preimage belongs to string, another to ring, probably the third linking number. So nevertheless, you was able to obtain some integer number using the conventional formula for Hopf index. So my question is, what's the meaning of this number, and how can one be sure that this number is conserved if infinitely distant points are not equivalent.
This number is definitely conserved irrespective of the type of of your far field in our case, because in all the cases which I showed and discussed regarding this hopfion rings or Skyrmion string, your far field is always a conical face. So it means that all this far field has a net magnetization pointed along, let's say, positive direction of the axis. So it means that in principle, you always can continuously convert this conical face towards the z-axis continuously. If you're able to do that, so then you can fix the boundary of this sample, the far field, everything remains continuous, and you directly plug this configuration and calculate the Hopf index using the Whitehead formula. There is no problem with that. But of course, you're right that if you plug this configuration as it is in our micromagnetic simulation into this formula, you will get a mess. But that's because this formula is not applicable for finite size sample. It assumes that you have infinite R3 space, right? So if you want to apply this formula to configuration which has been stabilized in finite size sample, you have to bring or at least you have to try to bring the edges to the same state everywhere. If you are able to do it continuously, then you are on the safe side.
Okay, so in order to compute this Hopf index, you first made this continuous transformation where far field is along
of the far field, yes, right.
Okay, but now the question, you can do it in different manners, and are you sure that you will obtain always the same number?
Yes, we're sure that in certain configuration, we always will get the same number, but definitely there are configurations, especially those which I called exotic configurations, like those, where we are not able to compute the Hopf index, despite the fact that on the either surfaces we clearly see the presence of this hopfion belt. We still cannot identify exactly the hopfion index following this procedure which I told you, but mainly not because we are not able to bring the far field and the XY plane to this configuration, but just because we are not able to make top and bottom edges of the sample equal to each other. And that's because this ring inside ring basically already touches the surface of the sample, and all this concept of the continuity is broken in this case.
Okay.
Okay.
You said it right. The very mathematical Volodia, she likes to probably ask you more questions later. With this, I believe we're at the end of the Q&A. Oh no, Revas, you have another question? Well, maybe we'll do this last question from Revas. It's coming up. Takes 1 second for him to join us in the panel. Then he can ask his question. Revas, can you unmute yourself and ask your question? Yeah, go ahead. We don't hear you. I think you still may be muted, or you have some issues with the voice. Okay, maybe check out the microphone, what you have on. No, we still cannot hear you. I believe you can hear me, everybody, right? So it's not, I think it's some issues from Revas. Give him 1 second, a few seconds to see if he can figure it out. If not, we'll move on to the, can you connect to your audio? Not yet. Do you want to maybe type your question? I still not hear you.
How about now?
Now, perfect. Yeah, go ahead.
Yes. So thanks a lot for this very inspiring talk. Just a very naive question for the sake of my education. So the hopfions that you told us about, so there is quite a number of parameters. So if you make a backdrop to some textbook textures, let's say a skyrmion, so the simplest one, the Belavin-Polyakov skyrmion, is parameterized just by a single length scale, the skyrmion radius. So if you make a skyrmion a bit more complicated and go to a domain wall skyrmion, it's going to be the skyrmion radius and the domain wall width. There will be two parameters.
Yep.
And then there are, like, if you ask yourself what's the energy of a skyrmion, you can find it. You can get analytic expressions in certain simplified limits. What about the hopfions? Like, are there any obvious limits where?
Yeah, for sure.
The expression for their energy simplifies.
Since we are working with much more complicated functionals than Belavin-Polyakov used for their solitons, we are limited in the number of answers we can give for this analytical model. So here, just for simplicity, I wrote the necessary but not sufficient condition for hopfion existence. Which is
you mentioned ABC greater than 0.
So all of them should be positive. But it does not mean that for any positive A, B, and C, the hopfion would have a size which is larger than the unit cell size. Because that's the micromagnetic approximation. We believe that it's absolutely continuous and magnetization is defined in any point in space. So in actual publication, we provide more precise answer to this question, where we, by doing the expansion to a certain condition to a very large hopfion, we identify the criteria to which this A, B, and C should satisfy to get a hopfion of a reasonable size. So we basically do so there are certainly a certain number of answers which can be driven analytically from analysis of these equations, similar way as it is done for Belavin-Polyakov soliton, for chiral magnets, for instance, for the periodicity of helical spin spirals in the critical field. The same is true for these models as well. And if you're really interested what kind of parameters we can derive from there, from this model, you can open our paper and you will find all of them there.
So there are some limiting expressions for this energy that you are showing us now in terms of A, B, and C, for instance.
Yes, absolutely, sure.
Okay, thank you. Thank you very much.
Okay, with this, I think I'm going to stop.